So, well, I'm taking it away. I'll just say quickly that all of our recordings are on the website, orangecountygov.com, sustainability. And we welcome you all to visit there because we have all of our March Madness meetings. I'm Kate Schmidt. For those of you who don't know me, I'm the Orange County Sustainability Coordinator. And I think we'll be taking Q&A as we go, so we don't have to wait for that. And we talked about credits. So I think we are thrilled to just say that we're having Jennifer here. She's team leader for the Clean Energy Siting Team at the New York State Energy Research and Development Authority called NYSERDA. She helps guide local government officials through best practices and appropriate local laws and permitting procedure for solar and battery energy storage. She's the one who's going to help us get local laws on new construction. She received her BA from Hamilton College with a concentration in geology and a minor in economics. And she holds a master's degree in education from Elmira College, as well as a master's degree in ecological economics, values, and policy from Rensselaer Polytech Institute. She's a certified energy manager and a lead accredited professional with a specialization in neighborhood development. So glad to have you with us tonight, Jennifer. Please take it away.
Happy to be here. All right, I'm gonna get my screen sharing. And again, there's only 2 of you, so feel free to interrupt me at any point with questions, or even say you can move this subject a little faster if you're not feeling all the detail or whatever.
Very casual tonight.
Yes.
Great.
Which screen did I share the right screen here? Let me stop 1 sec. I want to make sure I'm just doing the one. Screen 2. All right. You should be seeing.
Excellent. You're good.
Just a slide and nothing else. All right, cool.
Yes, thank you. Although I need to see if
all right, so like Kate said, I'm talking about battery energy storage today and some of the fire safety considerations that go along with it. Like I mentioned, it does say first responders. It's really hard to get Department of State to let us change the name of a course. It should probably say for code officials and others interested in fire safety, but here we are. So I'm gonna sort of breeze through these DOS slides just in case we wanna get Boris the credits. We kind of have to put these up before we start going, right? Course number, all of that, it's been approved, so I can't really leave anything out. We're all logged in. Don't log out if you want the credit for it.
Yep.
In the middle of it. Try to pay attention. I'll put some questions up on the screen for you to respond to, just little quiz questions throughout. I'll just ask you to put your answer to it in the chat box so we have a record of you being participating. Yes. Okay, so that's what that one is. All right, so now into the topic. So battery energy storage, we're going to be seeing a lot more of it. If your town hasn't seen it, it's probably only a matter of time before it does. Maybe not a large system, but it's certainly some residential systems, maybe some small to mid-sized commercial, and potentially even some large-scale industrial ones. And the reason for that is because obviously, as we transition away from fossil fuel energy in the state and in the country and in the world, and more renewables like solar, wind, hydro are coming online. Those are intermittent resources. They're not always producing energy right when you need that energy. So batteries can sort of suck up that excess electricity when we don't need it and hold it and push it back into the grid when we actually do need it. They serve a lot of other beneficial functions for the grid as well, but that's sort of the easiest way of thinking about it is, providing renewable energy even when the sun's not shining or the wind's not blowing. So there's going to be more of it, and they can be incorporated directly into a building. So like in a home or in an office or some other, building, and serve load directly on site. But they can also just be integrated into the grid itself, pulling energy in and out of the grid and just distributing it wherever it needs to go. So the batteries can be local or utility scale, sort of on the grid, serving the same sort of function like a typical power plant might. There are a bunch of different types of energy storage systems. You may be familiar with some. Pumped hydro, there's a great example of this in New York, and it's essentially using a large reservoir that's at a high elevation, and when electricity is cheap or plentiful, You use that cheap, plentiful electricity to pump water high up into that reservoir and store it, and then release it when you need more electricity, release the water to turn a turbine and generate electricity. So not a battery like you might typically think of one, but energy storage nonetheless. There are other types, mechanical, for example, compressed air energy storage, similar to the water example. You're using excess electricity to compress air and force it into a cavern or some other receptacle, if you will, and until you need it at a later time, at which point you release it to spin turbines and generate electricity again. So taking excess electricity when it's cheaper, storing it somehow and bringing it back. There are a few other examples on here, but the one we're really focused on today is electrochemical. That one's sort of on the middle left-hand side. And that's what you're typically thinking of when you think of a battery, you know, the batteries that are in your phone, laptop, car, etc. Electrochemical. Okay, so even within the electrochemical battery types, there's a lot of variety. And what we're seeing more often these days are lithium ion. That's what everyone's talking about. They're what energy storage is going to be most likely if you see it in your town. And some of the reasons for that, this chart is designed to sort of demonstrate why lithium ion is sort of winning out over the others. So they have a relatively high round trip efficiency. They have a reasonable duration. Some of the other types have slightly longer, but I think the other benefits of lithium ion outweigh that. And the quarter to 4 hours tends to be enough time for the purposes that we need them for. Similar time frame to build for the different types. The operating costs, however, for lithium ion are very low, which is a huge bonus, low operating costs. And the small space required is also a major benefit. They can pack a lot of energy into a very small space, again, which is why you're seeing them proliferate in our small technology gadgets, phones, laptops, et cetera, and now cars as well. And then finally, they're highly commercialized, right? All of the electric vehicles are starting to use them, and all of the other technology that I've mentioned a couple of times now. So widely available, relatively cheap, take up small space, et cetera. Lithium ion for, you know, the foreseeable short-term future anyway. All right, so here's our first little quiz question. And Boris, again, if you're trying to get credit, just try to pop your answer into the chat box there. So why are lithium ion batteries increasing in popularity? Is it A, because of their high energy density, declining cost, fast dispatch time, or all of the above? And I actually can't even see the chat right now. But
I was going to say, I'm looking for the chat box. More chat. Here we go. All right. I will say that is D, all.
That is correct. It is D, all of the above. Excellent work.
Woohoo! I'm paying attention.
Yeah. Yep. So this slide here just sort of demystifies what we're talking about when we say battery energy storage systems. The basic building block of them looks like any other relatively small battery that you're familiar with, like in your remote controls, your phones, etc. So over on the left-hand side, that's what we refer to as a cell, the individual little batteries, right? And when you take a bunch of them and string them together, you have a battery module. You start stringing a bunch of modules together, you have a battery rack, and one rack or even multiple racks, if we're talking a battery energy storage system. So it's really just lots and lots of little batteries wired together in one spot, designed to work together. Nothing too crazy there. The one thing that all of these systems that you're dealing with or might deal with in the future are going to have is a battery management system. This is really important. It's basically the eyes, the ears, the brains of the battery energy storage system. So all of these individual cells that you see over on the left-hand side of that last slide there, It can monitor every individual cell within the system, make sure that it's operating within the right temperatures. If one of them gets too hot, it will, send off an alarm to a monitoring station, and it can even isolate that one affected cell or perhaps one of the modules and sort of cut it off from the rest of the system to prevent overheating or whatever other issue happens to pop up. So the eyes, the ears, the brains, it can see what's going on. It can alert folks when something's going on, and it can even deal with the issue to some extent without anyone having to do anything, keeping everyone safe. Okay, so I briefly touched on why we're even talking about energy storage at the beginning, but we'll do a couple more examples here. So it can act as backup power in the event of a power failure. So that's one thing. It can sort of take the place of your traditional fossil fuel fired generators. You might have batteries in your house, the power goes out, you can start using electricity from your battery system. It can serve that same function, but sort of on a larger grid scale as well. I also mentioned that it helps with intermittent renewable energy power supplies like solar and wind that are not always generating electricity when we need it, et cetera. And so this chart here, the circle on the left there, just shows all of the different benefits that battery storage can have, both for customers in that like orange third. So, homeowners, business owners, et cetera. ISO services, which are the folks sort of managing how electricity is going around the grid and making sure that the grid is stable at all times. And then also utility services, the folks that are, building transmission lines and just generally making sure that the systems are all working as it should. So I won't go through every single example in here, but you can see, and like in the top left, for example, backup power being one function that they serve. If you follow that down, the different like inner circle layers are showing whether that particular benefit applies to transmission, distribution, or behind the meter, like in an individual building, for example. So you'll see if you go to backup power and start following down into the middle of the circle, you'll see those dark gray areas where it says service not possible. And those pertain to like, it's not really, backup power isn't really a function of the transmission and distribution grid, but it is a thing for like homeowners and businesses, for example. And then there are other benefits such as energy arbitrage, which is on the top right of the circle there. And you follow that one in and you see it's not blocked out anywhere because that can, that's something that can benefit someone that's just in their own building, again, a resident or, a commercial business owner, but it can also serve that same benefit to the transmission and distribution grid. And energy arbitrage is sort of what I was describing earlier, where when there's excess electricity or prices are higher or lower, you can choose to pull energy off the grid or push it back on using the batteries. Okay, so really trying to make this a little bit shorter than I typically do. Any questions so far?
Nope, all good.
Okay, great. So another example of batteries being great, and one of the reasons we're going to see more of them happening is because they're actually really good at replacing peaker plants. And so the way the energy system works now is we've typically had very large power plants that take a long time to ramp up, and it's not easy to ramp them up and ramp them down in accordance with the demand on the grid. So for example, on a really hot summer day when everyone's getting home from work and turning their air conditioning on and turning their lights on, and the office buildings are still running their AC and have all their lights on, that's a point in time where the grid is at peak demand. It's like the most power, on a daily basis that we might be using. And it's not efficient to try to crank up those base load power plants for just that few hour chunk of time, right? So we have what are called peaker plants that are able to more easily fire up and down to meet the fluctuating energy demand on the grid. They have typically been natural gas. And while natural gas is decent at that, it has emissions, and batteries actually can do the job better. So a gas peaker plant might be functioning at like 80% of its capacity, and it has minimum operational limits, right? Energy storage, on the other hand, batteries, not 80% capacity. You can think of them as having the capability of 200% capacity, because not only can they serve the function like the gas peaker does of pushing energy into the grid at those times of peak demand when it's needed, but it also has the capability of pulling excess energy off the grid when you don't need it. So that's how we sort of look at it, as having a 200% capacity. So it wins out over gas peakers in that way. The utilization rate for gas peakers is pretty low. They're only turned on to meet those peak demand or other sorts of emergencies. Otherwise, they're just sitting around doing nothing, being a cost, right? Energy storage, like we looked at in that circle chart on the last slide, has many other services. It can function as a gas peaker, but can also do other things to keep the grid happy. So lots of benefits. Dispatch time for a traditional gas peaker might take minutes to fire up. That might not sound like a lot, but it is when you're trying to avoid a blackout, right? And batteries can be up and running within seconds of flipping the switch. And then of course, gas peakers have costs and emissions associated with them. Energy storage, no costs, no direct emissions. So just one great example of why we're going to be seeing more. Okay, so now for the fun stuff. We've learned a little bit about how they work, and now I think what most folks are interested in is what happens if there's some sort of failure and maybe, you know, a fire or an explosion might happen, something like that. You've probably heard some of the horror stories about the Galaxy Note on airplanes, or like the hoverboards catching fire, things like that. Lithium-ion batteries have gotten a little bit of a bad rep in the press in that way. So one thing that can happen with them, with lithium ion in particular, is what we refer to as thermal runaway. And this chart on the screen here just sort of shows the process for that. So something starting at about the 12 o'clock part of it, something will happen to the battery, some sort of battery abuse. It could be, you know, puncturing it. Maybe a car runs into it and punctures the battery. Maybe it's very hot and it starts to overheat, or some sort of other, you know, battery abuse happens that the cell cannot handle, and it starts to heat up, and it might start off-gassing. So we're moving around to like the 3 o'clock section of the chart there. When that happens, we're still considering that to be in the preventative region, the green region. There are things that you can do to prevent it from actually catching fire once it starts that off-gassing. If you don't, you're going to start seeing smoke and eventually start seeing fire. And now we're in the red containment region, which is larger. So you're not able to be preventing the fire from happening anymore, but there are many things you can do to contain it if it is happening. And many of those things are shown here on this slide. And again, if you start at the 12 o'clock mark and just sort of work your way around, we're starting with the first things that you want to do to prevent things from happening, like having a great cell quality, like high quality batteries, right? And then good environmental system controls. You want to make sure that the room they're in is not going to get too hot or too cold. From there, you want to make sure you have a battery management system. That's the eyes, the ears, the brains of the system that we talked about before. So those are like your first basic 3 things to prevent anything from happening. Even if battery abuse does happen, these are the things that will, you know, isolate that cell and cut it off so it doesn't continue to overheat and so on. And then as you work your way around the circle, we're just sort of progressing and backups to the backups, right? So God forbid that the battery management system is not able to isolate that abused battery, if you will, in time, and it does begin to off-gas. You have off-gas detection in place to notify someone that that is happening. From there, maybe temperature monitoring. If it continues to increase in temperature, you want alarms to go off and some way of dealing with that. Smoke detection, lower flammability limit for gas detection. Lithium ion batteries do not release flammable gases as a normal course of their charging and discharging, but when something goes wrong and they start to overheat and catch fire, at that point, they actually can start to emit those types of gases. So we want that sort of gas detection in there. Exhaust and deflation venting systems, fire suppression systems, you get the idea. We're just sort of working around, if this thing fails, the next thing kind of covers it, and so on. And I think this chart, in my opinion, kind of just summarizes all of the safety features that are incorporated into the New York State Fire Code now, which is great because they are all good things. And so this is probably a good time to talk about that. So back before 2019, the state fire code did not have much in the way of requirements for battery energy storage systems. Call it, I don't remember exactly how long it was, but maybe say 1 page of requirements for energy storage systems. And it was not adequate, as you can see. So after hearing, the hoverboard things, the Galaxy Note, and there was one particular instance in Arizona, I believe it was in like early spring of 2019, where a large utility scale energy storage system, so think multiple shipping containers full of batteries down in Arizona, something went wrong, and the alarms are going off, and the fire department shows up, and they're not properly trained. They had never, been properly trained in how to respond to one of these. And so they see some sort of like white smokish stuff coming out of the containers, and they just kind of let it go for a little while, trying to figure out what to do, let it go, let it go. I think they might've even hung around for a couple hours first because there were no flames coming out or anything like that yet. And at some point they decided to go in. And so a guy walks up and opens the door to the energy storage system, again, like a shipping container size full of batteries. And as soon as he opens the door, there's an explosion, it blows the firefighters like 50 feet away. Not great. Since then, some analysis has been done as to what went wrong. And I don't remember every little thing that was part of the report, but essentially those systems were built, that system was built to an older code that did not have all of the safety precautions that we have in our current code now. And the firefighters were not trained in how to deal with it. If they were, they might have known not to go open the door and introduce oxygen into a container that had just filled with flammable gas, right? So training can go a long way. We're trying to do all of that. And to that end, back in 2019, right after that incident occurred, we worked with Department of State to get basically an emergency amendment to our fire code. And it's now the most stringent in the country as far as battery energy storage safety is concerned. So we got that in as a supplement real quick in 2019, and became a permanent ruling later on that same year, and then was finally fully incorporated into the 2020 New York State Code, which is great. So all across the state, any future systems have to be built with all of the safety measures, many of which we're going to go through today, and which I teed up on that circle diagram. So yeah. I think we're in a very good spot now. There were lots of lessons learned in the past, and we're hoping to avoid all of those with our wonderful, wonderful fire code. Okay, so most of the rest of the presentation is going to be going through the specific requirements that are in the fire code. Can get a little dry. I do my best to try to keep it interesting. Okay, so right now, we're going to be talking mostly about non-residential systems, so commercial and utility scale systems, just to set the stage. And then later on in the presentation, we'll talk about residential toward the end. Okay, so the scope of these systems is shown here. And so any battery energy storage systems that exceeds these thresholds, that triggers the fire code to apply, and they have to start following the requirements in the fire code. So for lithium ion batteries, any system over 20 kilowatt hours is going to be subject to the code requirements that we're looking at now, which is not very big. So it's essentially everything, right? Your laptop, maybe not so much, but any other system, yes. And it's not just for lithium ion batteries. The fire code applies to all of them. So you'll see the capacity, the threshold capacities here for other types as well. Like for lead acid, anything over 70 kilowatt hours, it's going to trigger the code, and so on. I don't know why this keeps doing that to me. I apologize. Okay. So the first requirement that applies to all those different types of batteries are construction documents that will need to be submitted along with any permit application. And so individual communities don't necessarily need to adopt this. It's already part of the fire code, which is great. So if you're looking for a permit, you should be getting all of these things from the applicant. Location and layout diagram, details of all the fire resistance ratings of the assemblies. I'm not going to read through every single one of these. Most of them are fairly self-explanatory. Basically, you're going to want to see all the different fire safety things that are included, commissioning and decommissioning plans. That's pretty important. You want to make sure that the system is going to be tested properly before it's put into, like, plugged in and turned on, right? And decommissioning in particular, really important to make sure that there's a plan for removing the batteries safely at the end of their useful life, or perhaps at the, you know, after an incident that renders some of them non-functioning anymore. Okay, the hazard mitigation analysis is a requirement for what we've defined as tier 2 systems. So larger systems, anything over 600 kilowatt hours. So we're talking like medium, large scale commercial on up. They will all have to do a hazard mitigation analysis per the requirements in the code. This is probably done by an engineering firm, and this basically just allows the permitting authority, you know, the community, to determine the best approach on what to do if there is a failure. So the hazard mitigation analysis just basically shows the consequences of any of the failure modes, some of which I queued up a little bit before. So if there's thermal runaway happening in a single energy storage rack, you know, what's going to happen? Like, how does this system handle it? What happens if the ventilation system fails, and so on? And the analysis needs to show, in order to be approved, all the things that you see on the right-hand side of the screen there, for example, that fires will be contained for the minimum duration of the fire resistance assemblies around them to allow people to get out of the building. So you're not saying that, you know, a fire can't happen. You're saying if fire does happen, you want to make sure it's going to be contained long enough to get people out safely. Also, it needs to show that toxic and highly toxic gases that might be released during the fires will not reach concentrations in excess of those levels that might be dangerous to the life or health of folks in the building before they have time to get out of the building. And then finally, that any flammable gases will not exceed 25% of the lower flammability limit and will be controlled through ventilation. So preventative measures, right? And if the hazard mitigation analysis shows that all 3 of those things are met, you can proceed. And again, this is only for those larger systems over 600 kilowatt hours. On top of that, the larger systems need to undergo large-scale fire testing. And UL 9540A is basically a testing protocol. And in summer, and it would be done by, you know, an approved testing laboratory. But essentially what they do is take a representative energy storage system, whichever, you know, the one that someone is proposing to install, and they try to force it into thermal runaway and try to induce a fire. And it's sort of a multi-step process. So if they force a cell into thermal runaway and nothing happens, cool, great. This is a very safe system. Most of the time, if you're going to force it into thermal runaway, you probably are going to create a fire. So they're forcing the systems to catch fire and then basically seeing what happens. And so if during the test, it shows that, you know, forcing one chunk of a system to catch on fire does not spread to a system that's adjacent to it. That's great. And the results of this large scale fire test can be used for the code official to approve exceptions to certain requirements in the code. And there are a lot of them, as you'll see in some of the coming slides. There are many code requirements that are like, you know, you shall have at least 3 feet of space between 2 chunks of a system, right? So that there's some separation between them so that if one catches fire, it won't propagate to the one next to it. However, if the large scale fire testing shows that this particular system is safe enough to have, for example, 2 feet apart, the code official can make that exception based on the results of the large scale fire test. That's one example. There are many more. All right, quiz question number 2. What is large scale fire testing not supposed to demonstrate? That a system will never catch fire, that if it does catch fire, it won't spread to an adjacent unit, or that the unit will contain a fire for the duration of the fire resistance rating. So which one of those is large scale fire testing not supposed to demonstrate?
All right, let me get to chat.
Any takers?
That would be A.
That's right. We're not trying to show that it's never going to catch fire. We're just trying to see what happens if it does. If the fire does happen, the system's designed to keep everyone safe anyway and not spread. And I'm just looking at the participant list and it looks like we had someone else join us. So welcome, John. Okay, another super fun code requirement, I like this one a lot, is fire remediation. So this essentially says that if an incident does occur in the system, that the owner is responsible for not just removing the damaged equipment from the premises to a safe location after the first responders have done their thing, but the owner is also required to dispatch fire mitigation personnel to essentially babysit the fire or babysit the system rather, and relieve the fire department of its duties. So one of the interesting things that happens with lithium ion batteries and other batteries possibly as well, is that even after you've been able to snuff out a fire, they can sometimes reignite hours even after the fire has been put out. You don't want your whole fire department to sit around and waste their time babysitting an energy storage system just to make sure that it doesn't catch fire again. So that responsibility is on the system owner to provide someone to do that until they can get the batteries out of there, which is great. Another great part of the code is the peer review requirement. So basically, if the AHJ needs it, which many of them probably will, I don't know too many communities who have an energy storage or battery expert on staff. So the energy storage system owner is responsible for providing services of either a registered design professional or a special expert to perform as a peer reviewer when an application comes in. Basically providing a technical expert to the permitting authority to help review the application, someone who knows the technology in and out. Okay, I mentioned this earlier. Another requirement for all system types is a commissioning plan. Obviously, you want to make sure that the system is installed properly and tested prior to turning it on. You want to make sure it's installed according to the manufacturer's specs, test all the components, make sure there's a training plan for the facility and operating staff, identifies personnel who are responsible for responding to incidents, those folks that we just talked about that can not just relieve the fire department of their duty, but also maybe provide some guidance in the event maybe they have some folks that maybe didn't get training. And that plan needs to be approved prior to initiating or turning the system on. And the report needs to be approved even prior to the final inspection. And part of that commissioning plan is also the decommissioning plan and an operation and maintenance documentation. Okay, so the operation and maintenance manual needs to be provided to the owner and the system operator prior to the system being put into operation. Sort of a common theme there. There needs to be a copy of the operation and maintenance manual on site somewhere. That doesn't mean you can't email digital copies all around to everyone who wants it, but there needs to be at least one copy on site. And what's going to be in there is obviously what it sounds like, all of the required maintenance, the contact information, set points, and then inspection, service, and testing schedules and logs to have a record of, when the system has been serviced. And the decommissioning plan, like I said, it's part of the commissioning plan. Prior to decommissioning any system, the authority having jurisdiction needs to be notified prior to that starting. And the plan should include a description of the activities that would take place to remove a system from service. At the end of its useful life, you might be removing an intact system from service. It's just not needed anymore, but perhaps more importantly, that plan needs to outline how you're going to go about removing a system that was damaged by fire or some other event. Sort of the unexpected decommissionings, if you will. Okay, and if we remember back to that circle diagram where we were starting with, cell quality, all of the equipment, not just cell quality, but all of the equipment, the code requires it to be listed, meet certain specifications. And so, like, for example, UL 9540 is the standard for energy storage systems and equipment. There's an exception for certain lead acid systems, but generally speaking, all of these need to have the UL 9540 certification. The chargers, inverters, and the energy storage management system might be included in that UL 95.4 listing, or they might be listed separately under separate UL numbers. And anytime you're changing a system after the fact, if you're not doing a perfectly identical repair, it's going to be basically treated as if you were, applying to build a new system, a retrofit. And it would trigger all the code requirements all over again. Okay, I've talked about this a couple times, but it's really important to remember that it's there and what it does. The energy storage management system, the eyes, the ears, the brains, it monitors, not just monitors, but also balances the system within the manufacturer's specifications. It's looking at cell voltages, currents, temperatures. Like I said, if one cell starts to overheat, it can isolate that cell and sort of shut it down and prevent anything from escalating. It should be able to disconnect electrical connections to the energy storage systems or otherwise place it in some sort of safe condition if it notices something going wrong, like a short circuit or over or under voltages, things like that. It's not something we want to fail, but there are other backup systems even beyond this. Okay, might seem obvious, but one of the major code requirements is that all of the enclosures for these energy storage systems, they need to be non-combustible. There are some general installation requirements. There should be an electrical disconnect installed near the main electrical service. And if that's not possible, there needs to be some sort of signage placed at the main entrance telling you where that disconnect is located. One thing that is interesting and good to remember about these, especially for firefighters, is that you might want to be careful about shutting down the system. If there's no clear sign of fire, it may not always be the best idea to just shut it down. Depending on the purpose of that particular energy storage system, it might be serving some very critical equipment. and it may not be necessary to shut it down. If you're not able to get direction from the folks, those like expert emergency contact information folks that the system owner provides, if you're unable to get direction from them for some reason, of course, the safest bet is probably to do the shutdown, but it's not always necessarily the first step. But regardless, in the code, that electrical disconnect needs to be at the main entrance, or otherwise you should be easily directed to it. Working clearances. Clearance for working on all of the energy storage equipment should be 3 feet. Obviously, they should be unobstructed. Fire departments might go out to do a site visit, and if so, they should notify the owners of the equipment if they're not in compliance with the regulations. These are fairly common. Some of these are fairly common sense things. You need to be able to access and maintain the equipment. Fire resistance rated construction. So any room or other indoor area containing energy storage needs to be separated by a firewall from other areas of the buildings. In certain cases, energy storage is allowed to be in the same room with the equipment they support, but generally speaking, they're going to be separated and closed off. Seismic and structural design. You want to make sure you're not going to be exceeding the floor loading limitation of the building, or if there's an earthquake, you want to make sure that it's going to be able to handle that, much like you would any other type of major equipment. Nothing special here, other than they can be pretty heavy, so it's good to remember. Where appropriate, you need to have vehicle impact protection, so you can see that in this example on the screen here. Just want to make sure that vehicles, not just cars, maybe forklifts, depending on where you are, want to make sure they're not going to be able to accidentally drive into the system and cause the batteries to puncture and start that thermal runaway process that we talked about early on in the presentation. You don't want to store combustible materials in the same room as the energy storage systems. For obvious reasons. If those combustible materials catch fire and it transfers over to the energy storage system, you have an even bigger problem. So combustible materials are not to be stored in the same room as the battery systems. Any energy storage systems that release toxic gases during charging, discharging, and normal use need to have some sort of hazardous exhaust system installed. Like I mentioned before, lithium ion batteries in particular do not release toxic gases during their normal operations of charging and discharging. So this is one of those areas of the code that will not end up applying to lithium ion batteries. But for many other battery types, it is a thing, and they need to have that exhaust ventilation. There are signage requirements all across the board. There needs to be approved signage on all the entry doors to the energy storage rooms or areas, or on the outside of the enclosures if you have energy storage cabinets or outdoor walk-in units. Signage is going to tell you what's in there. It's an energy storage system. It will tell you what type of battery it is, perhaps lithium ion, maybe lead acid, or one of the other types. It should clearly state that there are energized electrical circuits. And then critically, at the bottom of the little graphic there, the fire mitigation personnel contact info. You always want to make sure that any first responders that are showing up can call up someone who really knows the system inside and out and can help guide them through what to do in the event of an incident. All right, quiz question number 3. What is not required on the signage for entry doors, for energy storage rooms, areas, cabinets, or walk-in units? Name of the company, who installed it, battery type, fire mitigation personnel contact info, or the energized electrical circuits label, which is not required. And John, I'm not sure if you were looking to get Department of State credits or if you just want to have fun and participate in the quiz questions. We're putting the answers into the chat box.
It's the first one, isn't it? I didn't see anything about the company name.
That is right. You do not, the answer is A. You do not need to have the name of the company who installed the system. It does not matter. The important name
it doesn't matter after that point, right?
Right. Yep. Don't necessarily care who installed it. We care about the fire mitigation personnel who's responsible for it now and can help you in the event of an emergency. That's right. Okay, some general installation requirements. There's some security requirements. Any room area and walk-in units where there's an energy storage system needs to somehow be secured against unauthorized folks from coming in. In many cases, that security is going to take the form of a fence for an outdoor system, for example. There's a lot of energy stored in there. You don't want someone who doesn't know what they're doing going in and messing around with it. For energy storage that's in some sort of occupied work center, that security would be locked, non-combustible cabinets. And those cabinets, if they're not in a separate room, need to be within 10 feet of the equipment that they're supporting. You can choose to put energy storage systems on open racks, as long as those open racks here, not enclosed, they're open for, ease of operations and maintenance. You don't have to open doors to get to them. But if that's the case, they need to be in a separate equipment room that's locked off where only authorized personnel can have access. So walk-in units should only be entered for inspection, maintenance, and repair of the energy storage equipment. Otherwise, there should never be a human inside of them. One of the things one of the reasons that is good is because if there is an incident and emergency responders show up, they can be fairly certain that there's not going to be people inside of these shipping containers, these systems, because they're only ever going to be accessed for maintenance. Otherwise, they're locked off. So we advise, unless you have a good reason to think that someone is in there, just stay out. Don't want a repeat of that Arizona incident that I talked about earlier. Okay, so now we're going to start talking a little bit about electrochemical storage system protections that are required based on the location of the system, which we'll discuss a little bit later. Okay, so some of the electrochemical energy storage protections, in particular, size and separation. So they need to be segregated into groups that do not exceed 50 kilowatt hours each. And each of those groups of batteries needs to be separated by a minimum of 3 feet from other groups and from walls within the room or area. You'll notice coming on this slide and coming up, we'll have some red boxes that are showing exceptions or possible exceptions to those requirements. The first one shown in that red box below is lead acid and nickel cadmium battery systems that are, I'm just going to read it this one time, in facilities under the exclusive control of communications utilities and operating at less than 50 volts and 60. If they're in accordance with NFPA 76, they are exempt. I couldn't tell you exactly why those particular systems are sort of grandfathered in like that, other than I know they've been using those batteries for many, many years. I think they have a very good safety track record. So communications utilities have an exception to many of these requirements. That's why I said I'm only going to read it this one time. we'll refer to it going forward as like the lead acid communications exception, if you will. But then finally, larger capacities. So you could have groups larger than 50 kilowatt hours or separation distances smaller than 3 feet if that large scale fire testing that we talked about earlier shows that it's safe to do so. So this is one of those cases where the code official can grant an exemption based on the results of the large scale fire testing. Maybe you say up to 100 kilowatt hours per unit and 2-foot separation, just as a hypothetical example, if the large scale fire testing shows that that's safe to do and that a fire in one will not propagate to another. Okay, maximum allowable quantities. So this chart in the code just shows what it basically what it says, the maximum allowable quantity based on the different technology types. So lead acid batteries, the first one on the list here, there is no maximum quantity that's allowed for any one system for those. However, again, we're going to be mostly focusing on lithium ion. That's what you're most likely to see. The maximum allowable quantity for those is 600 kilowatt hours. But you can go beyond that if the large scale fire testing shows that it is safe to have a system larger than that. So that's where that first number 1 in the red box here says, where approved by the code official, systems that exceed the amount in the table can be permitted based on the hazard mitigation analysis and the large scale fire testing that we talked about before. So anytime you want more than 600 kilowatt hours of lithium ion batteries, it's going to trigger that hazard mitigation analysis and that large scale fire testing. Number 2 is that lead acid communications utilities exemption. They don't have the maximum allowable quantities. And then finally, dedicated use buildings are also exempt by default from the maximum allowable quantities cap. And that's just because those are buildings that have nothing but batteries in them. They don't have, people living in apartments on another floor or people working in an office building on another floor. It's just batteries. The risk to, human safety in those cases is very low. So dedicated use buildings don't have that requirement. Okay, quiz question number 4, true or false? For lithium ion battery systems exceeding 600 kilowatt hours, hazard mitigation analysis and large scale fire testing are both required. True or false?
True.
That is right. Thank you. The answer is true. If you want to go over 600 kilowatt hours, you're going to do both of those things to show that it's going to be safe to do so. Okay, so probably not too common, but in some instances, you might see different technology types in the same room. And so to determine the maximum allowable quantity of those, if you have more than one, you can't just say, oh, well, the max for lithium ion is 600 kilowatt hours. And the max for, let's say, flow batteries is 600 kilowatt hours. So that means we can have 1,200 kilowatt hours worth of batteries in a room. No, you sort of do a weighted, I don't know, like weighted average sort of, if you will. And that's just what this equation here is showing. So even if you were to combine those two types, like lithium ion and flow batteries, it's still a max of 600 kilowatt hours. You don't get to double it up just because you're mixing battery types. That's all that it's showing. Okay, there's an elevation requirement. Energy storage systems cannot be on floors more than 75 feet above the lowest level where the fire department vehicle can access, nor can they be on floors located below the lowest level of exit discharge. This is another one with some exceptions where the fire code official can approve installations on higher or lower floors based on testing results and if they feel comfortable with the safety features and things like that. Not really an exception, but just sort of a different use case that we'll see later is Rooftop systems are allowed, but they have their own set of requirements. But otherwise, inside the building, you don't want them too high or too low to be able to respond to an emergency. Okay, fire detection. There needs to be some sort of automatic smoke detection. If that's not possible, maybe it's like an open air area and you wouldn't be able to have the smoke build up enough. You can have some sort of radiant energy sensing or heat sensor for fire detection system. So one or the other there. And all alarm signals need to be transmitted to a central station. And so those central stations they're used to monitor the fire alarms and make notifications to the fire department if they need to, that, you know, a signal is going off and something's wrong. And for the most part, those central stations are going to be located off-site somewhere and monitored remotely. There are some fire suppression system requirements in the code. They either need to have an automatic sprinkler with a minimum density of 0.3 gallons per minute per square foot, or a rate of flow as determined by that large scale fire testing. Or there are some whole slew of other options as well that are not just automatic sprinkler systems. And you can see them, different clean agents and things like that. Okay, so this slide here shows some of the different fire suppression systems you might see: water, perhaps gas, perhaps both. Folks often, I've encountered this many times in doing this training or presentation, people are afraid to associate water with lithium-ion batteries because they've heard that water reacts with lithium in a very bad way. And that is true for lithium metal, but for lithium ion, you do not get that same reaction. And water is actually going to be one of the best ways to put out a fire for lithium ion batteries. It will render the batteries completely useless going forward, but I think the fire was going to do that anyway. So water is actually a really great way to deal with lithium ion fires. Not just because it will put it out right away, but because it's going to actually cool the battery down enough so that there's less of a chance of it reheating and reigniting after the fire has gone out too. Puts it out and cools it down to prevent any reignition. And in some cases, you might want both, like the picture on the right. Maybe you have a gas suppression system to snuff out any flames, maybe in a different piece of the equipment in the room. And secondary, the water, if the primary does not do the trick. Okay, some outdoor systems, it might make sense to use a dry standpipe. It can get pretty cold here in New York, and we wouldn't want the water in the pipes to be frozen should an emergency occur. So sometimes you will see a dry standpipe that can be filled by the fire department upon responding to an incident. There's a maximum enclosure size for outdoor walk-in units. It was originally just those dimensions that you see on the screen, 8 by 53 by 9.5 feet. That was a little restrictive in shapes. So the code requirement now is just no larger than 4,028 cubic feet. And it's not that you can't have a system that takes up more space than that. It's just that if you're going to have it all in one container, after that, it's no longer an outdoor walk-in unit. It would just be treated as if it's a building, like any other building, once it surpasses those dimensions. Do we have any questions? I just saw John pop up. Wasn't sure if you're trying to ask something.
You're dangerous. I can tell you that.
Well, I think what I was trying to get across anyways, I mean, they can be if the proper safety precautions are not taken, or if first responders are not trained properly. But I feel very good that all of these little pieces of the fire code that we're touching on here really do provide a great level of protection. We've only had it for a couple years. So, you know, some horror stories that you might have heard from large energy storage systems in the past, even as recently as 2019. I hope that all of our strict fire code requirements prevent them from occurring again. There's a lot in it that was not there before.
They just had a house fire in Monroe. It was started by lithium-ion battery from a saw charger, burnt the whole house down. And water is the most dangerous thing with lithium, whether it's a battery or what, because lithium has dustiness, which is phosphorus, and it's very reactive. It's like a phosphorus bomb. I had my deals with that because it's magnesium. At a car fire, we put water on and the car exploded on us because we didn't know it was a magnesium motor.
Well, that might be true for some types, but to the best of my knowledge and everything I've learned from, you know, our consultants and folks, that the number one recommendation for putting out a lithium-ion battery fire is actually to use water and snuff it.
Okay, and on that note, they just had a car fire in Tuxedo, and the minimum amount of water you want to use is 20,000 gallons. They brought the car to the storage unit for the wrecking company. It went up 5 times in a matter of 4 days, all by itself, what we call runaway voltage.
That's pretty wild. I'm not.
Oh,
yeah, that is.
And because these are the engineers talking, get into the real world, it's a whole different ballgame.
Well, I mean, we're definitely doing our best to get everyone at least on a somewhat level playing field here and have a basic understanding, but I certainly do not claim to know everything that there is to know, not even close. And I'm sure there are exceptions and little tweaks in certain technologies and chemistries that can make a difference. So in the coming years, hopefully build out our trainings even more. And, you know, this is right now, we're just going through and covering the fire code requirements, right? Another training that we offer that is actually put on by a consultant of ours who was a lieutenant with a New York Fire Department, goes into a bit more detail on how to actually respond to the fires and exactly what to do, and training first responders and actual incident management. So he would be way better to speak to some of this probably than me. So we bring him in to help.
Can I ask something? It's Kate. Can I ask something with that? So that's an unusual example he just presented. Is there a line of communication between the fire personnel that are responding to this and the state? Just say, hey, we're the front lines, we're experiencing this. You can listen to the engineers, the consultants, but we're telling you this thing just ignited again 4 times autonomously. Is there any, 311 line that they should be calling, or is there a data management sheet that they should be completing? How it runs under perfect conditions in a factory, we all know is so much different than the burn time, maybe exposed outside, etc. So I'm just wondering, where's the communication there? And if it's not there with the front lines, it should be there. And then my next comment is about the recyclability. So you said once you do put water on it, then of course the batteries are done. And then they were done anyway because of the fire, as you said. But what does happen to these batteries, whether they're waterlogged or burned? What happens in their life thereafter? Where do they go? Where do they get separated? I'm hoping to whatever natural resources they have. Are they landfilled?
I think I caught most of that. You were very soft. It was tricky to hear, but there was a question about, communication between the state and first responders, when they have stories about things not going as planned. I'm not aware of a 311 number or anything like that. And I don't know that my team or NYSERD in particular would even be best to necessarily do that, but we have been starting talks with the Office of Fire Prevention and Control. I might be missing a word there. So they are starting to get involved as well and want to start helping doing training. I don't want to volunteer them as, the right place for that dialogue to take place, but it could be. The short answer is I don't know, but it should happen. It's a good point. Like, where are we going to be learning from the field, right? Someone needs to know. The obvious first contact is that fire mitigation personnel from the owner. They need to know if their batteries aren't responding as they're supposed to. Other than that, I'm not sure.
Do you know about City University collaboration? I'll forget it all now because I haven't thought about it. But Uptown, which school I'll forget, host a sustainability center, and years ago they started working with Con Ed and the City Fire to really get it off the ground and to make sure everyone was on the same page. I'll look it up now and get back to you. But I mean, a collaboration like that for upstate would be important, especially when you're dealing with volunteer firehouses, but certainly the cities. Again, it doesn't matter. It's just real examples to be reported. Just either contact us an email or, like I said, a data management form submitted quarterly of anything unusual. But I'm sorry, I interrupted you. Were you going to respond then about the recycling of it all?
Yeah, I don't know after they've been damaged by fire or water. I'm not sure if or how that affects the recyclability of them. But generally speaking, they are recyclable. And it's exciting because New York is getting a battery recycling center in Rochester. What's it called? Li-Cycle, I believe it's called. So that is, I'm happy to report, being addressed. Now, again, not sure after they've been damaged if or how or to what degree that affects the recyclability of them.
Well, once they've been compromised with a fire, you have a hazardous material incident now. That's what comes into place in DEC. We're not allowed to go near them unless we have self-contained breathing apparatus because of the chemical compositions.
Now, if that's the case, again, that should be memorialized somewhere. Where does the state, and I would think it would be partially NYSERDA, where do they get this information and learn and investigate from it? Like, how do they tap that?
Well, something has to come down from the Office of Fire Prevention Control. And we have to get trained because it's actually, somebody's going to get hurt. You got to be trained in this. And I only done this because I've been in the power field. I worked for Orange and Rockland in the powerhouse as 35 years electrician. We had huge lead acid storage batteries. Each room had 120 batteries in there. Each battery is half the size of a refrigerator. And we had to worry about hydrogen gas because that's very explosive. It's a hot day. It has to be air conditioned and ventilated.
Yep.
But that's lead acid.
Yeah, they are all a little different. And there's definitely a ventilation requirement for lead acid.
But what they showed there in that one picture where you had all these hybrid batteries in there, if we came to a fire like that, I'd be scared to death because that stuff's going to explode. I don't know if you remember Vietnam when they had these phosphorus bombs. It's exactly what that is. It throws out white shards and burns right through your skin.
That sounds awful.
And it keeps on burning. It doesn't stop.
Yeah, I don't know that anything is, probably everything is not perfect right now, but we're in a much better place than we were just 3 years ago as far as education and code requirements and safety precautions for this stuff. So I'm sure there's definitely more work to do and a lot of training to do. Yeah, I hear you. Definitely in a better place than we were 3 years ago, though. It's pretty good code.
It is called Sustainable SUNY. And again, it's Uptown and they work with Department of Buildings, FDNY, and again, it's just a hub of information. So I'm suggesting that maybe one of those are needed upstate or outside the city. I would volunteer our SUNY Orange, but we don't rock the renewable energy front. Sullivan County does, Ulster's doing some things. So I would imagine that would be great. Maybe a BOCES. All right, I'll stop talking about that. Thank you. Please continue.
All right. Yeah, I'll try to get through the remainder here. I know it can be a little dry just going through code requirements, but it's important to know what's in there and want to make sure we can get those credits out the door by covering all of the material. I'm going to try to breeze through. All right, so the vegetation control requirement, any areas within 10 feet of the system need to be cleared of combustible vegetation or other types of growth. This is another instance where large-scale fire testing can allow the code official to approve a reduced clearance beyond 10 feet, but otherwise 10 feet of clearance. There needs to be a means of egress for outdoor systems and in open parking garages. They need to be separated at least by 10 feet. There needs to be a 10-foot path. Okay, so some technology specific compliance in the code, and these are just excerpts of charts that are in there. I touched on a little bit of this before, but just looking through the different compliance requirements, and we will talk about these over on the left-hand side here. Exhaust ventilation being one, there's spill control and neutralization requirements, explosion control requirements, safety cap requirements, and thermal runaway requirements. And whether or not those sections apply to a specific type of battery is shown in the 4 columns to the right of that. So for example, you'll see the exhaust ventilation requirement, like we just mentioned like a minute or two ago in conversation, is absolutely required for lead acid batteries because they do off gas as part of their normal operations. It is not required over in the 3rd or 4th column there for lithium ion. They are not required to have exhaust ventilation because they don't produce the exhaust as part of the normal course of their charging and discharging. Explosion control, on the other hand, is required for lithium ion batteries because if something does go wrong and they start to overheat or catch fire, at that point, lithium ion batteries can start emitting explosive gases. So they definitely need explosion control features. Now, an option for explosion control for lithium ion might be some sort of exhaust ventilation, but they don't need the exhaust ventilation just as sort of a default operating thing. So this chart just outlines which requirements apply to which types of batteries, basically. All right, so going through each of them in just a little bit more detail, where it applies. The exhaust ventilation is to be designed to limit the maximum concentration of flammable gas to 25% of the lower flammability limit, or some continuous ventilation that's no less than 1 cubic foot per minute per square foot of space. They need to have standby power that will run for up to 2 hours. And this is another one of those systems that needs to be monitored by a central or remote monitoring station where that battery management system is going to be sending signals if something is not working properly. Obviously, you need a gas detector to know when to activate the ventilation system, especially if you're using that 25% of the lower flammability limit threshold. And it needs to make sure that the ventilation remains activated until the gas gets below that 25% lower flammability level, and be able to set off audible and visible alarms and transmit an alarm again to that approved location, probably somewhere offsite, that central station that's monitoring everything, and also be capable of de-energizing the battery charger, activating the ventilation, and again, have 2 hours of standby power, just like the ventilation itself. For batteries that have liquid electrolytes, lithium ion not being one of them, but many of the other types do have liquid electrolytes, they need to have some sort of spill control and neutralization. It needs to obviously prevent the flow of any spilled electrolyte from going to adjoining rooms or areas, and not just contain it, but also neutralize it to a pH between 5 and 9. Some of these systems, they can contain corrosives that can be up to, say, even like 1,000 gallons. So it's really important in the event of some sort of spill to be able to contain and neutralize it for everyone's safety. Explosion control is always a fun one. This is one where I pointed out that even though lithium ion batteries don't need the exhaust ventilation by default, they do require explosion control because they can off gas in the event of an incident where they're overheating or catching fire, right? So they need to have either, they need to have deflagration venting, which is like pressure panels. So basically, should an explosion occur, those panels will open and direct the explosion sort of up and away versus allowing the explosion to come where you don't want it to go, like out the front door of a system where there might be a person standing. So those panels direct the explosion where you would want it to go, where it's safe for folks. And they should also have deflagration prevention. So exhaust fans are an option, just like we were talking about on the slide before, where you limit it to 25% of the lower flammability limit. So these are sort of the two options for explosion control. Could even do both if you want. Any batteries that are vented, for example, lead acid batteries that have a hydrogen byproduct just as part of their charging and discharging process, so they're vented. For any of those types of batteries, they need to have safety caps that prevent any flames that might be near them from going back into the battery. So they'll let the battery vent out, but prevent flames from going in and making things worse. Okay, thermal runaway. This has come up a couple times now, but the energy storage systems need to be provided with some sort of device or method to prevent, detect, and minimize the impact of thermal runaway. Once thermal runaway has started, it can't really be stopped unless you essentially cool it down and stop the temperature from rising. It's basically a sort of a positive feedback loop where once a battery starts overheating, if you can think way back to the very beginning where there's some sort of abuse, maybe it's punctured, maybe it's just exposed to a high temperature and it starts overheating, and then it heats up enough to where the cell next to it gets warm enough that it starts overheating, and so on and so forth. So we need something to be able to prevent that from happening, or at least minimize the impact of it when it does happen. And you can see over in number 4 here on the right-hand side of the screen, one way you can do that is by dousing them in water and cooling them down so that thermal runaway feedback loop stops. All right, quiz question number 5. Do all electrochemical battery energy storage system types require the same fire safety requirements?
No.
That's right.
Nope.
The requirements vary based on the technology of the battery. Okay. So we were going through the requirements that sort of cover all of the commercial and utility scale installations, that all the requirements those will need to meet. And then there were some additional requirements based on the chemistry of the batteries. Now we'll talk about the section of the code that has different requirements based on the location of the system or where it's located. So the different sections they vary based on whether or not it's a dedicated use building, which means it essentially is only storing batteries and it's not used for anything else, or a non-dedicated use building, which is, as it sounds, anything that's not a dedicated use building. So maybe there's office space in there and you happen to have a battery energy storage system somewhere in the building. So non-dedicated use buildings are obviously going to have slightly more stringent requirements to meet than a dedicated use building because there are, human life safety concerns associated with them. Similarly, the outdoor requirements for systems that are outdoors near exposures are going to be a bit more strict than those for outdoor systems that are remote and not near anything else that could be affected if something went wrong. So that's how it's divvied up. Like I mentioned, dedicated use buildings, they're only used for energy storage. There should be no one going in or out that's not authorized personnel trying to do maintenance. There's one little exception where you can have up to 10% of the building area be an admin office, but it needs to have its own direct means of egress. So no one needs to be walking through the battery storage areas in order to access that admin area. So up to 10% could technically be office and still be a dedicated use building. Just another image of a dedicated use building with a cutout, just to get an idea of what they might look like, a little bit of scale. Again, non-dedicated use, contain energy storage, but more than 10% of the building is used for something else. This chart shows the different requirements that either apply or don't apply based on whether or not it's a dedicated use building. A whole lot of yeses in both columns here. The one that sticks out as a no is this maximum allowable quantities. I teed that up a little bit earlier on a previous slide. Dedicated use buildings are not subject to the maximum allowable quantities requirement. They can have more. Other than that, they pretty much all have to follow all of these things: the size and separation requirements, the elevation requirements, smoke and fire detection, fire suppression, etc. All right, quiz question number 6. For indoor installations, which of the following is not required for both dedicated and non-dedicated use buildings?
Maximum allowable. That's C.
That's right. John, I think we should have you join the team and help do these trainings.
Those are the batteries right there that we had in the powerhouse, and each room had 120 of them. They're huge.
That's a lot. And it looks like this is just one small snippet in whatever building
Right.
that is. So.
A rack like that is probably 3,000 amps.
It is no joke. That is for sure. But yeah, dedicated use buildings may exceed the maximum allowable quantities requirement. Sort of a no-brainer, energy storage systems should not be installed in sleeping units or in habitable spaces of dwelling units at all. We've sort of talked about this, but when a battery system fails, it is likely to release toxic fumes. That is obviously not very good for a human to be around. So they should just never be installed in these areas where people are going to be hanging out, especially sleeping. Okay. All of them need 2-hour fire barriers, walls and ceilings. In dedicated use buildings, those barriers need to separate that potentially up to 10% admin area and from the rest of the system. And in non-dedicated use buildings, the energy storage systems need these fire barriers around them to separate from any other part of the building that's not the energy storage part. For remote outdoor installations, they're remote if they have 100-foot clearance from basically anything that could be a hazard in another building, just the lot line in general, any public ways, combustible materials, etc. Any exposure hazard, it needs to be at least 100 feet away in order for it to be considered a remote installation. Anything else is thought of as an installation near exposures. And the compliance that is required for those varies based on whether they're near exposures or remote. Again, you'll see mostly yeses here to those requirements. The ones that stick out as no's is that remote installations, not near anything else, do not have to adhere to the size and separation requirements, nor do they have to adhere to those maximum allowable quantities. And that's
Could you
because,
go back one slide, please?
What's that?
Go back one slide.
Yep.
100-foot clearance from buildings. Huh. Okay, thank you.
Yep. Yep, so if you have that 100-foot clearance, you get a little bit more leeway. You don't have to comply with the size and separation or the maximum allowable quantities. A couple little exceptions in here too. So for installations near exposures, you'll see the little subnote here. In outdoor walk-in energy storage system units, spacing is not required between the units and the walls of the enclosure. So there's like little things like that throughout it. And for remote installations, if the fire code official approves it, those installations can forego the fire suppression system. Many may choose not to forego it, but you can if it's remote and not going to hurt anyone if it catches fire. Maybe the system owner would prefer to just let it burn out. But that's a decision the fire code official can make if they want to. All right, quiz question number 7. For outdoor installations, which safety requirements are not applicable if the installation is considered remote?
A and B? No.
That's right, it's both A and B. Remote systems can forego the size and separation and the maximum allowable quantities. So the answer here is D. Thank you.
Okay, good.
This is an example of what we think of as a walk-in container. It's basically this example here showing what is essentially also the maximum enclosure size that we saw on a previous slide, and just pointing out some of the safety features in a real world application that we've talked about. So you can see the security fence around the outside. These are about the size of shipping containers. Again, that sort of corresponds with the maximum enclosure size. You can see the nice clear pathway, the means of egress there, where the 2 little people on the left-hand side are wearing green. That also gives you some scale. You can see on the top of the containers over on the right-hand side, the HVAC units, maintaining proper temperatures in there to make sure that the batteries stay happy while they're operating. Some exhaust ventilation also going on. So just giving you a little example of what one of these might look like in the real world. Okay, and similarly, just another example showing you some of the safety features we've talked about. This is like a cutaway, just showing it from the top. You can see the battery racks, fire suppression system, energy management system, some HVAC features, control panel inverter, etc. So that's like what a typical walk-in unit might look like inside. Mostly batteries and then some other supplemental systems too. So an example of what we refer to as cabinets, also filled with batteries, just a little bit smaller, and typically seeing them installed outdoors. This is a cabinet system, and it's also a good example of that size and separation requirement not applying when the system is considered, this must be a remote system, right? It has nothing really around it, so you can have those individual units closer together. They definitely don't look like they're separated by 3 feet. Okay, so outdoor installation requirements, they need to have at least a 10-foot clearance from lot lines, public ways, buildings, etc. This is the same list we saw before, basically 10 feet from all of those different exposure types. In the red box, there are some exceptions to that. I don't know if we want to go through all of them, but just know that they are there. There are always some exceptions to be made in some of these. So like, for example, if the building that happens to be near the energy storage system, the building itself is made of non-combustible materials, maybe you can get closer to 10 feet to that building, closer than 10 feet to that building, as an example. Okay. Still in outdoor installations, for exterior wall installations, you're not going to be putting any units on there that are greater than 20 kilowatt hours. There can be multiple of the same units, but they need to be separated by at least 3 feet. And all of them need to be at least 5 feet away from doors, windows, other openings into the building. Once again, there's that possibility for an exception based on large-scale fire testing. So the large-scale fire testing might show that it's safe to put the units within 2 feet of each other instead of 3, or perhaps they can safely operate within 4 feet of doors and windows instead of 5. There are some special energy storage installation requirements in the code as well. So I did tee this up a little bit earlier, saying that rooftop installations are an option, and there are specific requirements outlined for those. And the same is true for open parking garage installations. Like many of the other lists of compliance requirements here, most of the items are yeses, no matter where they're located. This chart in particular is a little bit funny to me, because the only no's are for parking garages. They don't have to comply with the rooftop installations, and for rooftops, they don't have to comply with the parking garage installation requirements, which is a no-brainer. But it's very helpful to always have things, clearly laid out for folks to see what applies and what does not. And a lot of these compliance are the same things that we've been talking about before: those size and separation requirements, the maximum allowable quantities requirements, and so on. And then these extra little sections where there's something special for rooftops and open parking garages. Like many of the other installation types, they need that 10-foot clearance again. I won't go through every part of it, but the one that sticks out a little bit here is that second bullet: any portion of the energy storage system building that is elevated above the rooftop on which the system is installed. You need a 10-foot clearance from that as well. And so that's a little bit unique to these ones versus the other areas that we've talked about them being installed before. Once again, you have the red box showing how you can get some exceptions to the code. Won't go through every single one of them. Fire suppression system requirements. They're required inside the enclosure of a walk-in unit or on parking levels that are not open to the sky. So anything other than the top level of a parking garage. Once again, there's an opportunity for an exception if that large scale fire testing demonstrates that the fire will not impact exposures in open parking garages. Okay, so special requirements for rooftop installations. Emergency personnel needs to have stairway access to the roof. They need to have, once they get up there, access to the system, a pathway that's at least 5 feet in width. The system needs to be located away from the edge of the roof at a distance of no less than 5 feet or the height of the system. Obviously, you want the roofing materials under and around the system to be non-combustible. There should be some sort of standpipe, a class 1 standpipe outlet installed at the roof location so you can have water if you need it. And the system should be at least 10 feet from the fire service access point on the roof. You wouldn't want emergency personnel going up that stairway in the first bullet just to be head on with the energy storage system as soon as they open the door, right? So at least 10 feet away from that access point. For both rooftops and open parking garages, systems need to be more than at least 50 feet from any of the building HVAC air inlets. There's an exception where if you can have the system set up to automatically de-energize the ventilation system or like close the dampers, you can get closer to those air inlets, but otherwise it needs to be at least 50 feet. For open parking garages, the systems cannot be within 25 feet of exits. And there needs to be a fence or some sort of locked gate or other barrier to keep the public at least 5 feet away from the outside of the system. Okay, now we'll just go through A few things, I only have, I think, like 8 slides left, so bear with me. I think we're gonna be done in a reasonable amount of time. I just want to touch on some of the residential code requirements for energy storage too. To give you an idea of what they might look like, a typical residential system might be, these ones are maybe the size of a large suitcase. Perhaps you have a bigger house, and so you have 2, maybe 3 suitcase sized batteries, if you will. But just a nice little image to give you some context and see what they look like. There are some thresholds for residential systems, much like there were for the commercial systems that we've been spending most of the time talking about. So for them, this code restricts residential systems to 40 kilowatt hours if they're located within utility closets or other storage or utility spaces in the house. You can double that if you're putting it in a garage or some sort of other accessory structure, or if you're putting it on the exterior walls of the house or somewhere outdoors on the ground. Anything above that, you're going to be triggering the commercial code, essentially. Size and separation for residential systems. Each individual unit has to have a maximum rating of 20 kilowatt hours. They need to be separated from each other by a minimum of 3 feet. Many of these things are probably sounding familiar to you by now. And units that are installed outdoors on exterior walls need to be at least 3 feet from doors and windows. This picture with the picture on the right with the red X through it, we're just pointing out that that installation is wrong, because if you recall, energy storage should not be installed within living spaces of the home. Okay. Much like the commercial systems, residential also needs some sort of fire protection. So the code outlines that they need to be protected on the system side by no less than 5/8 inch type X gypsum board or equivalent on both the walls and ceiling of wherever it's installed. Attached garages containing the systems also need to be protected on the system side by some sort of fire resistant construction in accordance with section R302 of the code, which I believe is saying that it's like a 1 hour firewall, essentially. Residential systems need smoke alarms to be installed in the area where the energy storage system is installed. If for some reason smoke alarms can't be installed, you can do a heat sensor. Indoor installations that include batteries that produce hydrogen, like we were talking about for lead acid earlier, or batteries that produce other flammable gases during charging, they need exhaust ventilation, much like we had been discussing for the commercial system too. If they're going to be off gassing as part of their normal operation, they need exhaust ventilation. Again, lithium ion is not going to be doing that. And if there is potential for the release of toxic gases during their normal operation, those are always going to be installed outdoors, no matter what. All right, quiz question number 8, and then we're on to the final slide. So if a single family homeowner wants to install a battery energy storage system in their garage with a capacity exceeding 80 kilowatt hours, should it be installed in accordance with section R327 of the New York State Residential Code or section 1206 of the New York State Fire Code, which is applicable to those more commercial systems?
B,
so they're exceeding
commercial
80
code.
What's that?
It's B, it's commercial code. You're gonna
That is right, because they're exceeding that 80 kilowatt hour threshold, so they have to meet the more stringent requirements that are outlined in the commercial one. All right. We made it through all of the slides. I think we spent enough time that the Department of State credits should apply. So yay. Happy to try and answer any other questions. I think we got a lot of them out during the presentation too. And I think I probably have some follow-up and research to do on some of those. But if you do have some, I'll do my best.
I am good. I had my questions answered, so I appreciate if you follow up, but otherwise I think it was a great night of lots of learning.
And I'll also just flag, I guess, that on our website, maybe I should have kept my screen shared. But anyway, nycerta.ny.gov/siting, or if you just Google clean energy siting NYSERDA, our page will pop up, and our battery energy storage guidebook for local governments is there. And one thing that's nice about it is we included a full copy of all the applicable sections of the fire code in there. I know they can be tricky for some folks to track down, but we have a copy of the fire code in the energy storage guidebook, which is handy.
It was
Great.
very good.
Excellent.
Great.
Thank you so much.
I was a little late because we got back from a house fire, so that's why I was late.
That's a good reason.
That's a very good reason. And thank you for your service too, you know?
And
also, John or Boris,
Yes.
do you think, and again, Denny, if you think this was useful, if you want to talk to your, I need to know, I mean, you know, this wasn't such a bad night to pick. I mean, maybe Monday's hard, but unfortunately, a lot of people did not show up for registered. We should have another one of these. I lean on you more to see, how do I fill the seats? So Jennifer's always gracious with her time. The state wants to offer these trainings, but how do we fill the seats?